Walk into a mid-level engineering interview involving Python, and the conversation will eventually turn to object-oriented programming. Take a look at this class. On the left, we have three distinct method types. On the right, the prompt is simple. Explain the execution difference between them. Most developers answer by recalling the standard parameter names. Instance methods take self, class methods take CLS, and static methods take neither. This answer often falls short when an interviewer asks how these methods actually behave at the execution level. Reciting the keywords describes the syntax you type, but it doesn't explain how the interpreter handles the call. To truly master these methods, you have to look past the decorators and focus on the underlying pipeline of implicit argument binding. Implicit argument binding is the internal mechanism Python uses to modify function calls the moment before they run. When you call a method, Python intercepts the request and injects an invisible first argument into the function signature. Method decorators don't alter the internal code. Instead, they change which specific object Python places into that first slot during this injection phase. Identifying what Python injects clarifies how state moves through a class. This allows you to differentiate between data that belongs to a specific user and data that must be shared across the entire system. Consider a basic student blueprint. When we create a new student, Python allocates a unique space in memory for that specific object's data. When we call a method using object.method, it appears as a direct operation on that specific object. This syntax is a high-level abstraction. Python translates that instance call into a class-level operation. It automatically passes the object itself as the first argument. This is why you define self, the variable that catches that incoming data. This binding solves state ambiguity. Without self, the master blueprint wouldn't know which specific object's variables to access or update. Imagine a system where data is written to the wrong destination because there is no clear routing label to guide it. Instance methods prevent this by using the self-binding to manipulate isolated, object-specific memory. Sometimes, logic applies to the entire group. If every student shares the same school name, storing that name inside every individual object is inefficient. We store it once as a class variable. The @class method decorator shifts the focus to the class blueprint itself, bypassing the individual student instances. In this flow, the execution path bypasses instance memory. Python slots the blueprint directly into the CLS argument of the function. Because CLS binds to the class rather than an instance, the method can be called even if no individual objects have been created yet. This mechanic is the foundation of the factory method design pattern. Because it receives the class as an argument, it can serve as an alternative constructor, generating new instances from different data formats, such as a raw string or a database record. By binding the blueprint instead of the instance, class methods provide the tools to manage shared state and object generation. There is a third case, utility logic. A function validating a test score doesn't need to know anything about a specific student or the school's overall configuration. Using @static method removes the implicit binding process entirely. In this mode, Python passes nothing into the function signature. The static method is architecturally isolated. A strict barrier blocks its access to instance data and shared blueprint variables. When you call this method, the parentheses stay empty. There is no self or CLS injected. It behaves like a regular function. If the function doesn't require any class-related data, you might wonder why we keep it inside the class at all. It serves as a namespace helper. It belongs to the class conceptually, like keeping a calculator in a university office. The calculator doesn't need the university's records to function, but that is where it is most useful for organization. Static methods allow you to group utility functions within a class to improve readability without involving the class's internal state. To understand how Python enforces these different behaviors, we look at the C implementation underlying the language. In Python, these decorators are wrappers for descriptor objects, mechanisms that intercept how attributes are accessed during execution. These decorators don't change your function's code. They act as a routing system that determines how arguments are bound when you look up the method. A class method descriptor intercepts the call, routing the class object into the first argument slot before the function starts. Conversely, a static method performs no binding, letting the signal pass through exactly as sent, attaching no external data. Your logic remains the same, but the execution path is determined by these descriptors, which manage how data enters your functions. Mastering Python methods means moving beyond the syntax to see how these descriptors act as gatekeepers for your data flow. This matrix provides a clear view of how to choose between method types based on the data they need to access. Use instant methods whenever your logic requires data that is specific to one object, such as modifying a student's individual grade. Choose class methods when the operation affects shared data or when generating objects from different starting formats. Static methods are for utility functions that logically belong in the class but perform tasks without accessing instance or class variables. This approach to architecture ensures that every piece of data is routed and isolated with intention. By understanding the mechanics of implicit argument binding, you move past rote memorization toward intentional design, ensuring data is bound only where it is required.